Okay, this is a worked example of Kirchhoffs rule. You can see in the diagram in front of you, that's the problem that we're going to be solving. 2 batteries, 3 resistors. All of the information you need is given. We have a 9-volt battery and a 12-volt battery, and the resistances are underlined there in red. If you do have the Giancoli textbook, it's number 29 in chapter 19. So if you want to copy that circuit down to your notes, you can pause the video for a second and then we'll move forward and I'll show you how to solve. So this is the circuit all set up, and we're going to go ahead and label all of the parts there. And the first thing that you're going to want to do is to arbitrarily label your currents. And so the way that I'm going to label this today is like this. Current 1 is going this way. Current 2 is going this way. And they meet up over here at this junction, and current 3 will work its way down the middle, like so. The next thing we need to do is apply the junction rule, where the sum of all the currents going into the junction has to equal the sum of all the currents going out. And so since we have current 1 headed this way, current 2 headed this way, and current 3 headed this way through this junction, let's go ahead and take a look there. What I can say is that I3, that's the sum of the currents coming in, is just I3 is equal to the sum of the ones going out. Well, I1 and I2 are going out. So that's our first equation. The next part of Kirchhoffs rules you need to apply is the loop rule, which states that the sum of all of the voltages is equal to 0 around any given loop. So here's my first loop, goes this way on the top, and my second loop goes this way on the bottom. So loop 1 on the top, I'm going to start at the battery, and that battery happens to be 9 volts. This battery down here is 12 volts. And so I start with 9 volts, and I'm going to do this all in terms of voltage. So remember that V is equal to I times R. So I start at the 9-volt battery, and as I make my way around the top loop, the first thing I encounter is IR, right, the voltage of that first resistor, and it happens to be current 1 and resistor 1. Now if you remember the sandwich shop, you'd be eating up sandwiches, so you're subtracting voltage as you go across that resistor. As you make your way around past resistor 2, again you'd be eating up sandwiches, and voltage is I times R. In this case, the I is I3, and the R is R2, and that's going to be equal to 0. So let's plug the actual numbers in. I get 9 minus, and I'm going to put the number for resistance in front of the current, since I1 is actually our variable. So resistor 1 is 25 ohms, so I would have 25 I1 minus resistor 2 is 18 ohms, so I'd have 18 I3 equals 0. So that's the first equation that we've built with the loop rule. And I would do the same thing around the bottom loop. See if you can come up with this same equation by starting from the 12-volt battery and making your way around counterclockwise. So I start with 12, I get to resistor 3, which would be 35 I2, and again I'm eating up sandwiches, so that's minus. And then I get around to the middle, passing by resistor 2 as I complete that loop, and that gives me 18. In the middle is I3 equals 0. So that's my second loop rule equation. So far, these are the equations that I have. Now the next step is we now have 3 equations and 3 unknowns. Well, we don't want to do that. If you know how to do that in your calculator, I would say just jump ahead and go ahead and plug all that in. Otherwise, what you need to do is get rid of at least one of these variables, and we're going to start by replacing I3 everywhere you see I3, which would be here and here, you're going to replace that with I1 plus I2. I had already written this out on a sheet of paper, so I went ahead and just took a snapshot of it. So that's what I did. For loop 1, I went ahead and everywhere that I had I3, the set I3 in the original equation, I plugged in I1 plus I2, and then I distributed, as you can see. And so for the top loop, here's my new equation that I've come up with that is all in terms of I1 and I2. On the next slide, I'll do the same with loop 2. Here you see loop 2, I did the same thing. I replaced I3 with I1 and I2 and came up with an equation that's all in terms, again, of I1 and I2. So this is great because now we're down to 2 equations and 2 unknowns, much easier to tackle. So, 2 equations, 2 unknowns. The next step you have to do is solve one of the equations for one of the variables. It doesn't matter which equation, doesn't matter which variable. I chose loop 1 and I chose I1, but you could just as easily solve for I2. It makes no difference. So I went ahead and solved for I1, and this was the equation that I came up with here. And the next thing I did is I took I1 and I plugged it into loop 2 so that I could finally just solve for one of the variables. Again, here are just some screenshots of my work that I did. So I went ahead and plugged into loop 2 for I1, and you can see I did that right here. And yes, it is a bit messy, but you know, it's messy for sure. But you can figure that out. Just be very careful when you're distributing. Be careful with your signs. The negative numbers, you want to make sure you're carrying all that. And when I got to the very end, I ended up with this equation here. And I went ahead and solved that for I2. And I came up with my first answer here of 0.18 amps for I2. From there, you can just start to backtrack and plug in to find I1 and I3. And that's exactly what I did. I went back to that first equation that I solved for I1, and I plugged I2 that I just solved for back into that equation. To solve for I1, I went back to my junction rule, excuse me, and then just added I2 to get I3. So in the end, these are the numbers that I got for the currents through branches 1, 2, and 3. Your numbers might be slightly off. I did a little bit of rounding, but these do in fact match the textbook solutions for number 29 in chapter 19. And there you have it. Kirchhoffs rules.